Hello again, students. So this is going to be a very short lesson because we covered most of this when we were doing thermodynamics, and this lesson is going to be on conductors and insulators and semiconductors. As you well know, substances can be classified in terms of their ability to conduct electrical charge. So we can either have a conductor where electrical charges are free to move in response to electrical force, and if it's not a conductor, then it's an insulator. So a conductor is a material in which electrical charge can flow freely. Things like metals like copper, silver, aluminum, these are typified good conductors, while most non-metallic solids are said to be good insulators. Insulators, which are things like glass and rubber and air, are classified as insulators because they offer a lot of resistance to the flow of electrons, so there's very little flow of current in an insulator. Insulators tend to hold their electrons in place very strongly, where conductors tend to allow their outside electrons to flow very freely. Semiconductors are a third class of materials, and they have properties somewhere between those of insulators and conductors, and the most common ones are silicon and germanium. They used to be used in making microchips, and now they're used in a wide variety of fabrication of a lot of different electronic devices. If you remember, when we talked about thermodynamics, we said that heat tended to flow from a hotter object to a cooler object. Well, similarly, or analogously rather, in a conductor, electrons tend to flow from a negatively charged object toward a positively charged object. And here you can see the pictures of heat moving from a hotter to a colder, and electrical charge moving from a negatively charged object to a positively charged object. So the difference between an electrical conductor and an insulator is really related to the atomic structure. The electrons orbit the nucleus, as you know, in the electron cloud, and those in the outer orbits experience a weaker force of attraction to the nucleus than those do on the inner orbits. So consequently, the outermost electrons, and those are the ones you remember from chemistry we call the valence electrons, they can be dislodged really easily, a lot more easily than the inner ones. In a good conductor, some valence electrons become detached from the parent atom and wander more or less freely throughout the material. You may also remember this in metallic bonds as the sea of electrons, and they don't really belong to any one particular atom. The exact number of electrons detached from each atom really depends on the nature of the material, but it's usually between 1 and 3. When one end of a conducting bar is placed in contact with a negatively charged object, and the other end is in contact with a positively charged object, then the free electrons are able to move easily from the negative end and toward the positive end. This goes back to our basic rule of electricity. Opposites attract, and like charges repel. And this ready movement of electrons is the hallmark of a good conductor. So in a good conductor, the situation is really different, for there are very few electrons free to move throughout the material. Most electrons remain bound to that parent atom, but without these free electrons, there's very little flow of charge. Okay, so how do you give something a charge? Well, an ebonite rod is a rod that's actually made out of a very hard rubber substance. We'll be using one of these to do some demonstrations, hopefully if we have time. And when you take an ebonite rod and you rub it with something like fur, and then you put that in contact with a metal object like a sphere, here in this illustration, some of the excess electrons from that rod are transferred to the object. And once the electrons are on the metal sphere, then what they do is they tend to repel each other and spread out over the sphere's surface so that they even out. You notice in part B of the picture, the sphere on the left has a negative charge that's distributed over the surface. And in a similar manner, the sphere would be left with a positive charge after being rubbed with a positively charged rod. In that case, the electrons would move from the sphere onto the ebonite rod. This process of giving one object a net charge by placing something in contact is known as charging by contact. Now, it's also possible to charge a conductor in a way so that you don't actually have to involve contact. So in this picture, we have a negatively charged rod, and you bring it close to, but do not touch a metal sphere. So in the sphere, the free electrons closest to the rod move to the other side. They're running away. This is what we call charging by induction. And I want you to remember that charging by induction means bringing nearby. Induction, we're inducing a charge by bringing something nearby. Okay. As a result, part of the sphere nearest the rod is going to become positively charged, and the part furthest away from the rod has become negatively charged. So these positive and negative regions have been induced or persuaded to form because of the repulsive force from the negative rod. So the free electrons, remember, move over to one side. Now, if the rod's removed, the free electrons return and everything goes back to normal, just like it was, and the charge regions appear. So under most conditions, the earth is a really good electrical conductor. So when a metal wire is attached between a sphere and the ground, as you'll see here in part B, some of the free electrons leave the sphere, and what they do is distribute themselves in a much larger earth. So this is called grounding, and if the grounding wire is removed, followed by this ebonite rod, then the sphere is left with a positive charge. This process of giving one object a net electrical charge without touching the object to a second charged object is called charging by induction. And this process can also be used to give a sphere a negative net charge if you do the reverse, if you bring a positively charged rod nearby. Then the electrons would be drawn up from the ground through the ground wire onto the sphere. Okay, so a process similar to charging by induction in conductors also takes place in insulators. Now, we've been talking about giving a charge to a conductor. Now we're going to switch gears and talk about giving a charge to an insulator like plastic or paper or maybe even a wall. So in most neutral atoms or molecules, the center of the positive charge coincides with the center of the negative charge. In the presence of a charged object, though, the centers can separate just slightly, and they result in more positive charge on one side of the molecule than the other. In other words, they realign themselves. This effect is known as a polarization, and it's just a realignment of charge within individual molecules, and it produces an induced charge on the surface of an insulator. This is why you can hang a balloon on the wall. If you take a balloon and you rub it on a wool sweater or a cashmere sweater or your hair, okay, and you bring it nearby a wall. Now, by the way, the wall's got to be dry. But if you bring it by a near wall, then the charges realign themselves in the wall so that more positive charge is facing the negatively charged balloon, and it induces a slight positive charge. So we have polarized the wall. This works best on the ceiling tiles, and I'll show you a demonstration of this. Also, you can bend water. If you rub a balloon on your hair and bring it near a stream of water, the actual water will bend. So that brings us to the end of this very, very quick lesson where we describe conductors. Conductors, remember, are those objects that allow a free flow of electrons throughout. And an insulator is an object that really holds the electrons tight and does not allow a free flow of charge like glass, plastic. Good conductors, things like silver, gold, copper, aluminum. Good insulators, air, glass, and plastic and rubber. And then you have semiconductors, remember, like germanium, that are used to produce electronic devices. And conductors, they're the ones that we use in copper wire to move electricity from one place to another. The other thing that we discussed very quickly was the physical process of charging by contact or charging by conduction, where you actually move electrons from one device to a conductor. Then you have charging by induction, where we give a conductor a charge by bringing another charged object nearby, but not touching. So remember, induction, charging a conductor by bringing an object nearby. And then finally is polarization, where you have a realignment of charge in an insulator. So remember, polarization deals with insulators, and it's like an ebonite rod attracting paper or being attracted to a wall. So the question is, can you give a charge to a neutrally charged object? And the answer is yes, you can do that by induction or by polarization. So that ends this lesson on the conduction and conductors.